For sure. Good evening. Good afternoon, everyone. Yeah. If you have any specific question, you may ask regarding last module. Basically, this analysis of laminates and failure of laminates. How many people have joined? Maybe one. Only one, yeah. Maybe others will join up. Yeah, good afternoon, Shushan. No, anisotropic mechanical characterization, see, like we have discussed, I think in details, uh, lamina, which is orthotropic. I mean, it's orthotropic means it's a special case of anisotropic only. Okay? It's not isotropic. Now we have also discussed in details how to characterize a lamina, starting with its from macromechanical analysis. That means we showed that we need 4 independent elastic constants, and then we have also discussed what are the corresponding engineering constants. Like for a lamina, orthotropic lamina, we need E1, E2, nu12, and G12. And then I told you that in our micromechanical analysis, we have also discussed some of the experimental standards by which we can determine this E1, E2. Okay? So that is what is characterization basically. I mean, in the laboratory you can measure these things, and once you know E1, E2, U12, G12, you can actually find out the what is called so-called that stiffness or compliance matrix. Okay, because as you know, 1 by E1 is nothing but S11. Okay, 1 by E2 is nothing but S22. So like that, we have all the relationships, and that is what is characterization of orthotropic lamina. Anything else you want? I think this is what you are asking. Did I make it clear? Bidirectional, I have not. Let's see. I mean, if we just consider this is another thing. Like we may have woven fabrics. I have not discussed that because finally we have restricted our discussions to that laminated composites made of unidirectional lamina. Okay. But bidirectional characterization is not that. I mean, in fact, in many cases, bidirectional is easier. If you consider woven fabrics, okay, many times E1 is equal to E2. If you have, however, there are other dimensions to that. That is not in the scope of this lecture. Like we have braided composites, like it is actually woven in defined angles. It may not be 90 degree, but that is not in the purview of this course. Other than that, bidirectional means what? You have maybe number of lamina in the some fibers in the 0 degree and some are in the 90 degree. If they are equal, then you will have E1 is equal to E2. That's what it is. In lectures, module 6, lecture 3, for example, reinforcing factor is given. No, you don't have to calculate the reinforcement factor. I mean, the reinforcement factor actually depends upon the fiber shape, size. I think I have given some, say for circular, so it's 2, or for rectangular it is 2 A by B. So you don't have to calculate that. That will be given, okay? Because as I told, those things are actually calculated conducting some experiments and some by some curve fitting techniques, and therefore these reinforcement factors you don't have to calculate. In the problems, that will be given. Okay, reinforcement factor will be given. You don't have to calculate that. Is it clear, or you still have some issues with the reinforcement factor? If there is a problem, if in any example, this will be given. Okay, you don't have to calculate that. Assignment 7, question 7. Let me see what was that. Okay. Two laminates with identical dimensions made from same glass epoxy laminate with same lamina thickness but with splitting sequence. One is 090 90 0, another is 90 0 0 90 are subjected to the same axial tensile load. Which of the following is true? See, why I have asked this question was with an objective. If you remember, while discussing ABBD matrix, if you look at the expressions for A, expressions for B, or expression for D, I have clearly mentioned that you can interpret like elements of A actually do not depend upon the stacking sequence. If you just go back and see what is A is nothing but sum over Q bar into thickness, sum over all the layers. That means Q bar for each layer multiplied by the thickness of that layer and sum over all the layers. That is A. Therefore, A does not depend upon the stacking sequence. It only depends upon what is the Q bar matrix for a particular lamina and its thickness. That's all. So whether it is 0 90 90 0 or whether it is 90 0 0 90, A matrix elements of A will be same. Okay, that is why I have put this question. And the mid-surface strain actually depends upon A matrix, isn't it? For a symmetric laminate, you can decouple it. That means M is equal to A into epsilon, where epsilon is the mid-surface strain. Therefore, it does not depend upon the stacking sequence. So 0, 90, 90, 0 and 90, 0, 0, 90 both will have the same mid-surface strain. That's why I have asked this question. Is that clear? Okay. Shravan Kumar, is it clear? Could I make it clear? A matrix depends only on the Q bar of each layer and the thickness of each layer. You multiply these two for each layer, sum over all the layers, that is A. On the other hand, if you look at B and D matrix, those two actually depend on the stacking sequence. Suppose you take these 0, 90, 90, 0 and 90, 0, 0, 90. If you change the stacking sequence, then your D matrix will be different. In this case, this symmetric laminate, therefore D will be 0. Otherwise, if it is not a symmetric laminate, suppose I take say 0, 45, okay, 90. In one laminate is 0, 45, 90. It is not symmetric. And another laminate is 90, 45, 0. For these two, A matrix will be same, but your B and D matrix will be different, because B and D matrix, if you look into it, it actually involves the terms like Z square, Z cube. What is Z? Z is the distance of a particular layer from the mid surface. Zk square minus Zk minus 1 square in B matrix. In D matrix, it is Zk cube minus Zk minus 1 cube. Therefore, it depends on stacking sequence. On the other hand, A does not. Elements of A do not depend upon stacking sequence. Is that clear? Okay, fine. So this is very, very important. You must know this. That is why this is the basis for quasi-isotropic laminate. Under in-plane, because A matrix is like an isotropic, therefore it behaves as quasi-isotropic. And I told you also that in quasi-isotropic, 0, plus 45, 90, 135. 135 means minus 45. Okay, it's quasi-isotropic. Even if you change their positions, it is still quasi-isotropic, because A matrix does not depend upon that. 0 plus minus 45, 90, or 0, 90 plus minus 45 will have the same A matrix. Sir, for composite repair, if you change in time, you should quickly see if you explain this function. What is composite repair? No, you see, you cannot change for a particular component. What are the ply orientations actually are decided already depending upon the strength and stiffness requirement. Suppose if you have 0 plus minus 45 90 symmetric laminate, each of these lamina has its specific function to perform in the load bearing. I told you, I am repeating again because this is very, very important. 0 degree provides strength and stiffness along x direction. 90 degree provides the required strength and stiffness in the y direction. Plus minus 45 degree provides required strength and required shear strength and shear stiffness. Okay, as you know, plus minus 45 degree provides the highest shear stiffness. So if we expect that this will also have to take some kind of intense shear load, then this plus minus 45 degree layers are required. So you just cannot replace at your will. Suppose you have a composite, you have a laminate 0 plus minus 45 90. If you think, okay, I think because it's plus minus 45, you cannot just make it 0 plus minus 30 90. The stiffness and strength will be different. Is that clear? And when you talk about repair, I am not sure what repair you are talking about. Repair in composite is little difficult, unlike conventional metallic materials. Okay, like in metallic materials, if there is some kind of defect, there are many techniques like welding and all. This doesn't work in case of composites. Is that clear, Mr. Shravan Kumar? Scarf repair. Scarf repair. I'm not sure what you are talking about. See, in no repair, we change the, whatever is the repair, you cannot change the ply orientation. See, because as soon as you change the ply orientation, I think by this time you know, as soon as you change the ply orientation, its characteristics change. You know? I mean, so please explain quasi-isotropic level in more elaborately. Given plus quasi, also quasi-isotropic. See, the definition of quasi-isotropic is there should be at least 3 layers. There should be at least 3 layers, and if there are 3 layers, the difference in ply orientation of the successive layer will be pi divided by 3. That is 0, 60, 120 is a quasi-isotropic laminate. Okay. Now, why it is? I think I have discussed in details that finally you can show that if it follows this, then its A matrix is like an isotropic. What is isotropic? A11 is equal to A22, and A66 is a function of A11 and A12. Okay, this is a function of, like, that is, it behaves perfectly like isotropic under A plane. Now 060, your question is 045, 90 minus 45 is quasi-isotropic. So if we have 4 layers, the difference in the successive angles should be pi by 4. Pi by 4 is 45. So if the first layer is 0, second will be 45, third will be 90, fourth will be 135. 0, then 0 plus 45, 45, 45 plus 45, 90, 90 plus 45, 135. This is a quasi-isotropic laminate by its definition. Now 135 is nothing but minus 45, isn't it? If you consider an orientation with respect to x, if it is 135 in the anti-clockwise direction, in the clockwise direction is 45, isn't it? Therefore 0 plus 45, 90 minus 45 is quasi-isotropic. But what I was stressing upon was, even 0, if you change this sequence, 0 plus 45 minus 45, 90 is also quasi-isotropic, because A matrix does not change. Elements of A matrix remain exactly the same. Even 90, 0 minus 45 plus 45 is also quasi-isotropic. So this is why it is that. What 0, 60 minus 60, same thing. If it's a 3-layer laminate, the first ply angle is 0, second is pi by 3, that is 60, third is 60 plus 60, 120. Now if you take 120 with respect to x in the anti-clockwise direction, in the clockwise direction it will be minus 60, isn't it? Therefore 0, 60, 120 is equivalent to 0, 60 minus 60. Now 0, 60 minus 60 is quasi-isotropic. Again, if you just put 0 minus 60, 60, that is also quasi-isotropic, because A matrix does not change. A matrix does not depend, elements of A matrix do not depend upon the stacking sequence. Why does the addition of 090 degree plies do not change the characteristics? Hello? Yeah. Why does the 090? See, 090 is anyway, 090 is free from any shear extension coupling. Okay, 090 is spatially orthotropic. Okay? Therefore, if you just put 0 and 90, I think you are talking in terms of, see, you say that for quasi-isotropic, the difference between successive plies 4 with 0 for the quasi-isotropic. Why is, oh, I am going to, who is that? Who is that? Vishal. See, I'll come to that one by one. First of all, the characteristics of isotropic is, as you know, it is actually free from any shear extension coupling. Okay? Now, we have shown that if you have 0, say plus 45, minus 45, 90, this is quasi-isotropic in the sense that under the in-plane load, the A matrix is like similar to isotropic, meaning if you look at the elements, A11 is equal to A22, and A66 is actually a function of A11 and A12, and A16, A26 is 0. This is 1. And then whether you make it 0, 45, 90, 135 or 0, 90, 45, 135, the placing of lamina, just now I think you joined late, Vishal, placing of lamina does not affect the elements of A matrix. Elements of A matrix, if you look into the A is nothing but sum over all the layers Q bar into thickness of each layer, Q bar K into Tk. Therefore, while it is placed, does not have any influence on A. Therefore, like because 0, 45, 90, 135 is symmetric, quasi-isotropic. So 0, if you change that there will be no difference in the, you can make 0, 90, 45, 135, A matrix will remain same. Therefore, this is also quasi-isotropic. The basic reason is, again I am repeating, A matrix does not depend upon the stacking sequence. It only depends upon the properties of each lamina and its thickness. And because the characteristics of A matrix actually define whether a laminate will be quasi-isotropic or not, therefore, irrespective of where you place the layers, it is quasi-isotropic. 0, 45, 90, 135 is quasi-isotropic. 0, 90, 45, 135 is also quasi-isotropic. Is that clear? If you want to get convinced, you can actually try to find out A matrix for both the cases, and you will see it is same, because nowhere it comes where 90 is placed. What is the distance of a particular lamina from the mid surface? Therefore, it will be exactly same.
One more doubt regarding inverse of A.
Let me first. We have time. Let me first. Mr. Vishak, is it clear? Yeah. Another aspect I would like to tell you, see, when you do this laminate analysis, basically we are not supposed to do it manually, but I have solved one or two problems just to make the steps clear. Okay, so even in the assignments, we have given you some problems. Those problems are chosen in such a way that you can do without using a calculator. Say, for example, if we wanted to find out, say, the first ply failure load for a cross ply 0-90 symmetric laminate, okay, subjected to NX. So immediately you might think that NX, NY, NXY is equal to A into epsilon X naught, epsilon Y naught, gamma X Y naught. And you need to take A inverse. It's not required, you know. If it's only subjected to NX, you can see it actually boils down to 2, because it's a cross-ply laminate. A16, A26 is also 0. Therefore, it actually finally boils down to a 2x2 simultaneous equation. You can actually solve it by hand. Okay, but finally, the main objective here is in the laminate analysis. Basically, it is not, we are not supposed to do it by hand. Suppose it is subjected to all general loads, all the 6 components of loads are present, NX, NY, NXY, MX, MY, MXY. Then you have to take the full inverse of the matrix. That you have to write a computer code and do it in no time. It's very simple. But here, the objective has been that you understand the steps. So whatever problems, whatever examples we have actually given in the what you call the assignments, it is doable without taking any inverse. You don't jump into taking the inverse. It's not required. Okay. You just see that if you put that A matrix into epsilon x naught, epsilon y naught, and gamma x y naught is equal to nx 0 0, you'll find that it is actually 2 by 2 simultaneous equations. From there, you can actually find out epsilon x naught and epsilon y naught. I hope I could make it clear, because many times you might think that in the assignment, how you take inverse and all, it's not required. So can we go with hybrid laminate with different ply orientation with different angles to show any marked difference? No, I think I have already told hybrid laminate. First of all, in some cases we do use hybrid laminate, but again, you see, you don't miss out the basics. In a laminate, what are the lamina? What all lamina will actually make a laminate? How do you decide? I have to repeat it a number of times. It's actually decided by our strength and stiffness requirement. Please take a note of it. Suppose I want a component which is actually subjected to only axial load. Only 0 degree plies are good enough. You don't have to do any other angle. Okay? You just make it moderately thick, giving maybe 100 or 200, depending on what is the strength and stiffness requirement. Strength requirement, you just put that many 0 degree plies, because we know that it has to only withstand load along x. That is good enough. Next, suppose it has to be strong and stiff, both x and y direction. Okay? Suppose they have to be equally strong and stiff. You have to put some 90 degree lamina, because that will provide you strength and stiffness in the y direction. And y angle lamina? Angle lamina, because 0 and 90 provides excellent strength and stiffness in the x and y direction, but they cannot provide shear stiffness and okay. So we go for angle lamina. Okay. So 0 degree, suppose we provide plus minus 45 degree, that also provides angle lamina. So what will be the, that also provides shear stiffness. So what will be the stacking sequence and layout? That is actually decided by the strength and stiffness requirements. So coming to your question of hybrid laminate, why should we go for hybrid laminate? What is hybrid? Suppose maybe we need glass and graphite hybrid, or we need say graphite and Kevlar hybrid. Why? So you must know why. Then only we have to go for hybrid laminate. Suppose, for example, this Kevlar epoxy has a better, impact resistance compared to say graphite. So what we do is, suppose we have a graphite epoxy laminate, say a quasi-isotropic graphite epoxy laminate, 0 plus minus 45, 90 symmetric laminate. If we expect that it might have to also, it will have to also, withstand some impact load. So the outer layers could be made with Kevlar epoxy. So we may put 2 Kevlar epoxy at the outer layers. Okay. Again, it has to be symmetric. That means 0 Kevlar, say then 0 graphite plus minus 45, 90 symmetric, and then this is a hybrid laminate. This outer Kevlar layer will provide resistance to impact. So that is why we need to go for the hybrid laminates. And we can find out, like see, if you have understood the steps of finding out the laminate characteristics, you can find out for hybrid laminate also. The only thing is Q1 will be different, that's all, nothing else. Just in general, for achieving maximum bending stiffness, we need to keep material far away from the bending axis, right? Any comments on what it implies? Now, suppose you are considering a beam, say. Suppose it's a beam. So we can consider this to be a one-dimensional stress. That means the bending stress is sigma x. Okay. Suppose it's the xz plane. So bending stress is sigma x. So naturally, we'll put 0 degree lamina at the outer layer, because bending stress will be maximum, isn't it? Suppose it's a plate which experiences bending in both the planes. Okay. Then there should be sufficient 0 and 90 degree layers at the outer. Away from the away from the neutral axis. Depending upon what kind of stresses we are expecting, okay? depending on what stresses we are expecting, so we must put the lamina which has the corresponding strengths to withstand those stresses. Like you see, why suppose 0 plus minus 45 90. So suppose again if you take the bending of beam, then the bending stress is maximum. At the farthest point. Of course, in one side is compression, another side is tensile, and shear stress will be maximum at the center. So plus minus 45 should be closer to the the neutral axis. Is that clear, Vishap? Mr. Vishap, is that clear?
First step to 90, 180 is also equivalent to minus 60.
Huh?
That
Why?
no, like that.
That I told. I have already told.
If the angles are same, 180 minus 60.
Same, yeah. So when we write the fiber angles, see, instead of writing 135, I can write minus 45. It's same because all the angles are actually measured with respect to x. Okay. So similarly, 120 is nothing but minus 60. Okay. Rather than writing 0, 60, 120, I can write 0, 60, minus 60. And there is another advantage of having plus minus 45, plus minus 45 actually plus and minus 45, any plus and minus theta is a balanced laminate. That actually eliminates A16, A26, that means shear extension coupling. Now somebody asked why 0 and 90, addition of 0 and 90 does not change the characteristics. It is 0 and 90 of course adds to the stiffness and strength, but suppose you have a plus minus theta laminate, it's a balanced laminate. And therefore, if you take a balanced symmetric laminate, so B is 0 as well as A16, A26 is 0 because if you subject it to in-plane load, there will not be any shear, in-plane shear. Okay, in-plane axial load does not cause any shear. Okay, if it is a plus minus theta laminate. Now add 0 and 90 to that. 0 and 90 anyway does not have shear extension. Therefore, that does not change the characteristics. So 0 plus minus 45, 90. This is anyway quasi-isotropic laminate. But in addition to that, suppose if you have only say plus minus 30 and say 0 and 90, you add 0 and 90, there will be no A16, A26. That means the shear extension coupling will be 0. That characteristics does not change by addition of 0 degree and 90 degree loads. I didn't understand how to calculate strains in assignment without doing inverse of matrix. Okay, right? So actually, no, just follow me and just. Is that clear? This is not always true. Please don't, take it for granted. But the kind of assignment examples I have given you, intentionally we have provided this where because it is 090 is symmetric, so A16 and A26 will not be there. Okay, and you have only NX. Okay, even if instead of NX it could be NY, still it actually comes to only two equations, two unknowns. Where NX is known, A11, A12, A12, A22 are known. Therefore, you can know what is epsilon x1 and what is epsilon y0. Is that clear? Also, I will tell you something else. Like if for 0 degree laminate the Q is given for 0 degree. Suppose you want to find out for 90 degree. You don't have to really use the transformation matrix. Only Q11 and Q22 will be interchanged. You know, that's what it is. So you must, by this time you might have understood that. Okay? But again, having said everything, finally when you do the laminate analysis, you cannot do it we do not do it manually. But here, just to make you understand the steps, we have given some problems where it is, without even using a calculator, perhaps you can do it. Okay? You don't need to compute it first. Is that clear? Let me know if it is clear. Nalini, is it clear? Yeah, so this is of course only for a special case. We have intentionally chosen those problems where it will be done. Okay? Because A16 and A26 are, otherwise it comes out with 3 by 3 and it becomes complicated. So we have given a special orthotropic laminate where A16 and A26 are 0. And if you want to, subject to NX, if you want to find out what is epsilon x, epsilon y, it's just a 2 by 2 simultaneous equation which you can solve by hand, solve manually. You know, you don't have to actually, because it's not expected. See, here the objective is not to find out whether you can do matrix inverse or not. That is not required here. If you have understood the steps, that is good enough. Yeah. Any other question? Assignment 6, question 4. Composites with 0 or near 0 coefficient of thermal expansion are desirable in space applications where the component expands wide range of temperature variation using the formula and the properties of the graphite fiber and matrix. Find out the fiber volume fraction. This is simple. You just put all those values here and find out what is BF. At what BF alpha 1 is equal to 0. The first line is given just to make you appreciate. Sometimes it is actually required in space applications that in a particular direction, the coefficient of thermal expansion is 0. That is a huge, achievement. If you can make it 0, what happens? I think in the one of the earlier classes I have told you that dimensional stability is an actually issue in composite materials. In space applications, suppose the range of temperature is very high, maybe say in some cases say minus 60 to say plus 60. So in that temperature range, depending on the coefficient of thermal expansion, it is very, very difficult to restore the dimension, to keep the dimensional stability, because the dimension will, the shape will change. So if we can make the coefficient of thermal expansion 0 or near 0, that means we can have the dimensional stability. So just to make you appreciate that, in this problem it is nothing, you just put all those values here and make alpha 1 is equal to 0, you will appreciate that in this case the answer, that means if we have these properties of the fiber and the composites, and if we make a lamina with 42% volume fraction, fiber volume fraction, it will have 0 coefficient of thermal expansion along direction 1, which is not possible in conventional metallic materials. Don't confuse it E1F, E2F. Like these are actually, sometimes the fibers are actually considered as transversely isotropic. In class when we have derived, we have considered the fiber to be isotropic, But you may have the fibers may have properties like which are transversely isotropic. That means E1F is the longitudinal Young's modulus of the fiber. Similarly, E2F will be transverse Young's modulus of the fiber. So similarly, alpha 1F, alpha 2F. So don't confuse with that. In this question, the formula is given, and again I am repeating. You don't have to remember this formula anytime. Okay, excepting I mean, very simple formula like say S11 is equal to 1 by E1. That you have to. That is not nothing to be by heart. If you have understood, then it's fine. Then maybe S22 is equal to 1 by E2. Other than that, this formula, whatever is required, will be given to you. Is that clear? How to calculate midplane distance Z and Z bar for a 3-layer laminate? Three-layer laminate. Yeah. 090 symmetry. I have to write I think. See, 3-layer laminate means okay. So the mid surface will pass through the central layer, isn't it? So if you actually try to find out what is ZK for this is one, this is Z1, Z2 is 0, and this is Z3. For the middle layer, it will be 0. That's all, because the middle layer, the mid surface of the middle layer and the mid surface of the laminate do coincide. Therefore, it's 0. And you can appreciate here that suppose the mid surface strain is epsilon x naught. Okay, for the middle layer, it is epsilon x naught only. I mean, if it is also experiencing curvature, then the strains of the other two will be different. But here it will be same because the reference surface actually passes through the this layer itself, this layer itself. Therefore, here it is 0 because Z2 is 0. Is that clear? See, generally we calculate at the middle surface, but you can always calculate at the top and bottom surface anywhere. Anywhere you can calculate. Only thing you need to know for finding out the strain at any point, you need to know the distance of that point from the middle surface. Yes. Any other question? So some of the things, like in the assignments, I have given you some problems. You might think that you have to. One thing I told you, inverse. It's not required. Most of the problems you have given in assignments do not require you to. You don't have to actually calculate inverse. Second thing, if it's a cross-ply laminate like 0, 90, if you know Q for 0, Q bar for 90 is very easy. You don't have to use transformation matrix. You just swap Q11 and Q22. Okay, even if you try to do using the transformation, it's fine, but it's not required. Okay, please post your. Sir, another point I want to ask: in CLPT, you have used Z and Z bar for distance from the plane. What is the difference between these two? Did I use Z bar in the CLPT? ZK minus 1. I think I have used. K matrix. Did I use Z bar anywhere in the CLPT? Can you see this? Can we see the module 7 somewhere or module 8? Just yeah, yeah. Modulate, yeah. Just the PowerPoint. That is good enough. Modulate. No? So can you just why I have used jet bar, Vishal? I'm not able to recall why I have used jet bar. In which maybe module, which lecture? Can you just specify? See, jet is only required to find out the strain at any point with reference to middle surface. That is one. And second, that we need to find out the A, B, and D matrix where Z is required. There, Z bar. I think only in B matrix somewhere I have written that is the mean distance. Z bar is equal to Z1. Can you just show me where it is? You have used Z and Z bar for distance from midplane. What is the difference? Z bar is most probably I have used to specify the distance of the mean distance. Basically, suppose if you consider the kth layer, there are two, one is Zk, another is Zk minus 1. So Zk is the distance of the top surface, Zk minus 1 is the distance of the bottom surface. And Zk bar is the Zk plus Zk minus 1 divided by 2. That is the distance of the middle of that layer, or that is called the mean distance. No, I remember. I think Z bar is the mean distance. Zk plus Zk minus 1 divided by 2. Zk is the distance of the kth layer from the top surface of the kth layer from the reference plane. Zk minus 1 is the distance of the bottom surface of the kth layer from the reference plane, and Zk bar is nothing but Zk plus Zk minus 1 divided by 2. Most probably we have used that while showing that for a symmetric laminate B is equal to 0. Most probably. I am not able to. If I remember correctly, Zk bar is the mean distance. Zk plus Zk minus 1 divided by 2. But anyway, that doesn't have any significance, Only thing you have to, for finding out A, B, and D matrix, you have to know Zk and Zk minus 1 for each layer. That's what. Even in fact, for A matrix, you don't need that also. A matrix only the thickness. For others, you need for each layer Zk and Zk minus 1. Zk is the distance of the from the reference plane, and Zk minus 1 is the distance from the bottom layer, bottom of that layer from the reference plane. I think Zk bar is the now where is Zk bar? No, that's what Zk bar is. This the mean distance for a particular layer. Zk bar is the middle of that layer. Yeah, that's what it is, if I remember correctly. So, any other question? The time is. We have time. Sir, please clarify the difference between cross-splice symmetric laminate and Symmetric laminate anyway understood. Symmetric laminate all of you know, I am sure. So I don't have to tell symmetric. That means with reference to middle reference plane, whatever is at the top, the same thing in mirror image is at the bottom. Okay, that is symmetric. Okay, that means for each layer at a, above the middle plane, corresponding to that, exactly at the same distance, there is at the other side there is a same identical lamina, that is symmetric. Say for example, 0, 90, 90, 0. So the which refers to the middle surface. Can I just write? Yeah. So this is 0, 90, 90, 0. This is symmetric. This is the reference, you know. So they are same material. That means for Q is also same for these two 0. Their thickness is also same. Similarly for this. Okay, this is symmetric. I think this is clearly defined. Okay. And what is crosswise symmetric is, now a symmetric laminate could be say 0, 45, minus 45, again minus 45, plus 45, 0. This is symmetric. What we write in short is 0, 45, minus 45, symmetric. Okay. Now cross-ply symmetric means the layers will be only 0 and 90. This is called cross-ply symmetric laminate. Sometimes also called specially orthotropic symmetric laminate, because all the layers are either 0 or 90. This is what is cross-ply symmetric laminate. What is the significance? This is a simple laminate where because all the layers are specially orthotropic, therefore there is no shear extension coupling. Okay? So this is cross-ply symmetric laminate. A symmetric laminate could have any fiber orientation. Okay, say 0. I mean, it could be plus minus theta 1, say plus minus theta 2, symmetric. Theta could be anything between 0 to 90. Okay, this is symmetric. However, or say theta 1, theta 2, symmetric. Theta could be anything, but when the layers are only 0 and 90, that's special orthotropic. This is sometimes also called cross-ply symmetric laminate. Is that clear? You mentioned about obtaining Q90 from Q0 in easy way. Similarly, is there any easy way to obtain? No. See, please try to understand. I did not ask you to follow the easy way. What I mean is, please appreciate that these kind of problems are not done manually. Okay? At every step, you need to have a computation. Like we actually have to have A inverse. You have to multiply by transformation matrices. Okay? But we have chosen some problem, some examples here where intentionally we have taken so that you understand the steps. Therefore, when I give you 090, it's easier. You can still do it using transformation matrix. But suppose you want to find out, given 0 degree, if you want to find out what is 90 degree, it is that just swapping between 1 and 2. But that doesn't have any, it is not true for all other. There is no easy way for others. Please don't try to do that. Finally, if you have understood the steps, I would maybe at the end of this course, you may write a small code either in MATLAB or in any other programming language so that you can actually analyze the laminate. Okay. But here what I mean is to solve the assignment problems to save your time. If you know for 0 degree, for 90 degree, just swap between 1 and 2. That's what. Yes. It's Nalini, 099, 0 is symmetric. Please go back to this. 090, 0 is symmetric. Zero, 90, 0 is symmetric. Now, it's actually a 3-layer laminate. It's a good question, why? So, the reference plane actually passes through the center of this layer, 0, 90, 0. This is actually written as 0, 90, we put a bar over just to show that is actually a 3-layer laminate, 0, 90 symmetric. You can consider this to be actually say you can consider that even though there are 3 layers, so this is one layer, maybe half of this is another layer, half of this 90 is another layer, so it's symmetric, you know. So 0, 90, 0 is symmetric laminate. Okay. You can just imagine that this is one layer of certain thickness, this is another layer, half of this, okay, and this is the reference plane, this is another layer exactly same, these two are exactly same, and this is another 0 degree layer, so this is symmetric. I think this is clear. Is that clear? Okay, thank you. You're welcome. Yeah. You're welcome. So thank you all for attending. Yeah.